Hi everyone, I'm Marius Vikhammer.
I'm Sudeep Mohanty.
And we're from the IDF core team. And today we're here to talk about low power applications on the ESP, the ultra low power coprocessor, or the ULP as we often refer to it. And we're from the software platforms department, more precisely the IDF core team. And as part of our responsibilities, we also have the ULP. Yeah, here's a brief overview of what we're going to be talking about. First, we'll give an introduction to what low power management means on the ESP32 chips. And then we'll talk a little bit about why ULP, what is the ULP, the different types of ULP we have in ESP IDF, and then how do you program it, a little bit about the different software support we have provided for it. And then we'll also give some examples about what kind of power consumption you can get while running with the ULP. And then to end it off, we'll do a roadmap, show some resources in case you want to learn some more. And then at the end, have a Q&A if there's any questions. Okay, low power management on the ESP32 chips. What does it mean? Well, basically, the chip is divided into different power domains. And we can either clock gate, lower voltage, or turn off parts of it to save power. This allows us to reduce the power consumption while also running the chip with partial capabilities. So as you can see here in this diagram, there's 4 main power modes provided in ESP IDF. You have the active mode, where everything on the chip is enabled. And then you have the modem mode, where we shut down the RF part of the chip. You can see the wireless MAC, the RF part. All of those are shut down during modem mode to save power. And then we have light sleep, which is pretty configurable, but it's mainly about shutting down the CPU. And then we have deep sleep, which is where you can have the lowest power consumption possible. And here, basically everything is shut off except for possibly the RTC power domain. And if you have worked with ESP IDF, you'll see this term RTC come up everywhere. And like originally, it just stands for real-time clock, but in Espressif world, it basically means the low power domain. So here we have a RTC memory, which is just low power memory that's not powered down when you go to sleep. And here, marked in red, you can see what we're going to talk about today, the ULP coprocessor, which is a part of the RTC power domain. Okay, so why the ULP? Let's consider an application, a pretty standard low power one. You have a sensor or something that you want to pull every once in a while. And then if your measurement is above a certain level or something happened, you want to do something with that measurement. So here in the flowchart, you can see like a typical application where you begin your ESP program, you initialize all your sensors, you measure, in this case, the temperature. If you're above the threshold, then you log this value over Wi-Fi. And then to run this off battery, you, of course, have to sleep. You can't just keep the CPU up and running because then you would empty the battery in a matter of, pretty quickly. So what you can do then is you go to deep sleep. You set a timer until it tells you to wake up in 1 minute. And then after 1 minute, you wake up the CPU again, take a new measurement, check the threshold. If not over the threshold, you go back to sleep again. And you just keep looping around here until your measurement is above the threshold and you take an action. But if you really want to save power here, then some parts of this are pretty expensive. Like waking up the main CPU, rebooting everything takes a while and takes a lot of power. And if you're running off a battery, this is not ideal. And then comes the ULP into the picture. Is there any way we can do this better? So what is the ULP? It's a ultra low power coprocessor, which means it's a low powered core that complements the main cores. And it can remain powered on while the main CPU sleeps. And it's from here you get the main power savage. and it's capable of handling simple tasks such as reading GPIOs and monitoring certain sensors. And then if the ULP sees that the measurement is above a certain threshold, it can wake up the main CPU. And the main CPU can then do whatever it needs to do. Currently in our chips, the ULP is available on the ESP32, the S2, and the S3. So basically our extensor chips. So here, now we have modified this flowchart to work with the ULP instead. So on the main core, you still do your initialization, you set up everything, and then you go to sleep. But instead of periodically waking up the main CPU and measuring, you let the ULP wake up periodically and take the measurement. That way, it's only the ULP that wakes up. And it wakes up much quicker, and it requires much less power. And then only when you actually need the main CPU to do something do you wake it up. And by doing this, you can extend your battery life significantly. Yeah. And now I'll give it over to my colleague, Sudeep.
Continuing with what Marius just introduced us to, we'll take a little bit of deeper dive into the features that ULP provides. The way the ULP is designed is that it will periodically wake up and perform a task. Now, this is controlled by the ULP timer. This timer can be configured by the main CPU during initialization. Also, the ULP core has access to this timer and can alter the timing values. So it's the ULP timer which will periodically wake up the ULP. The ULP will perform the actions that it's supposed to. In case it needs to wake up the main CPU, it will wake it up. And then it can go back to halt, or it can go back to sleep. And this process repeats. To make the ULP more competent, it has access to several GPIOs and some peripherals which are useful in designing an application. These peripherals are like the EDC, the I2C peripheral, and it also has access to the internal temperature sensor. Then the ULP has access to some memory, which is in the RTC power domain. This is known as the RTC slow SRAM. And this memory space is common between the ULP and the main CPU. So the ULP and the main CPU can also exchange data if needed. Of course, the ULP has access to all the registers that come in the RTC power domain, so it can control all required peripherals and GPIOs accordingly. Well, at this point, we can take a check and calibrate as to what the ULP is not. It's safe to say that it is a low-powered core. It's not a general-purpose core, which can, for example, run more complex programs or even an RTOS. It is limited in memory. It has, for now, access to 8 kilobytes of RAM to have its code and data. There is no JTAG debug support on the ULP core, so the debug ability is a bit limited for the ULP core. And also, there is no hardware floating point operations which are supported on the ULP core. So essentially, the ULP core will be useful for some trivial code which can help your application save power. Moving on. There are a couple of types of ULP processors that we have on ESP chips. The first one is called ULP FSM, or finite state machine. The second one is called ULP RISC-V. We'll go into the details of a bit about each of the types of ULP cores that we support. So the first type of ULP core is the ULP FSM, or the finite state machine. This is a simple low-powered core that was developed by Espressif. It has its own instruction set, and it has its own way of programming, and it can perform all tasks that ULP can, and this is the first kind of core that we have. This was first introduced in the ESP32, and it is also available on the ESP32 S2 and the 32 S3. The other kind of ULP core that we have is actually a full-fledged RISC-V core. Now, this was introduced from the ESP32S2 and is also available on the ESP32S3. It's a RISC-V core supporting the RV32IMC instruction set, and it's much more user-friendly. We will look into the differences between these two in terms of programmability in a bit. Some things to note here is that we cannot use both the ULP FSM and the ULP RISC-V cores simultaneously. And we'll take a look at what kind of how we program these individual cores. First up, how do we program the ULP FSM core? There are actually two ways in which we can program the ULP FSM. Since it has its own instruction set, this is compiled using bin utils, and it kind of looks like assembly code. If you look at the image on the right, you will notice that the code resembles normal assembly code, and this is the first way that we can program the ULP FSM. Another way to program the ULP FSM core is by using C macros. So this is a special kind of programming guide, per se, where we can embed some assembly-like macros into C code, and then load these as a binary into the ULP. This is, let's say, a bit more easier to read as compared to assembly code if you're not familiar with it. But this is another way that ULP FSM can be programmed. Moving on to the ULP RISC-V. This ULP RISC-V is coded or is programmed in plain C language. We're all familiar with this. This is compiled using the RISC-V toolchain that comes with Espressif's ESP IDF. And this is probably would be more familiar to people who are used to programming in C and working with IDF for other applications. So the obvious, let's say, the differences between the FSM core and the RISC-V core is their programmability. Let's say there's no additional step that is involved in programming ULP. The way we have built ULP applications is that it's just a one-shot process. If you're familiar with how we build applications on ESP IDF, this will feel no different. There are a few steps that are needed to ensure that the ULP binary is compiled first, and then this ULP binary is converted into an binary array, which gets embedded into the main application binary. And this main application binary, which runs on the main core, loads the ULP binary during runtime. And from a user's perspective, it will be just a one-shot single command, idf.py build flash, and you should be able to build your ULP code and your main code together. Let's go a bit into the highlights of the software stack that is supported for ULP. So there's a ULP driver that comes along with ESP IDF. This driver basically provides access for the main CPU to control the ULP core, and also provides access for the ULP core to access different peripherals that the ULP has access to. For example, the GPIOs, ADC, I2C, and temperature sensor. Some of these drivers are not yet built, and they are in the plans. Also, there are certain utilities that are shared between the main core and the ULP core, such as a locking mechanism for synchronization. And there are other utilities which help the ULP core perform its activities, and all of these are part of the ULP driver that comes with ESP IDF. The best way to learn about ULP are the several examples that we provide with ESP IDF. These touch some of the basic aspects of what ULP is capable of. For example, how to pull a GPIO, how to talk to a sensor on ADC, for example, how to use print statements if you need to, and so on and so forth. So these examples are present in ESP IDF and will be one of the best places to start learning about ULP. Okay, so at this point, I will hand over the baton to my colleague Marius to take us through the power consumption that we see with ULP.
Okay, now we have seen how we can use the ULP, but we also want to see what actually kind of power consumption we can get with it, right? Because that's the whole point here, to save power. So we have taken some rough power consumption numbers, and you have to remember that these are heavily influenced by software parameters. Like our different sleep modes are very configurable, and we're always tuning everything to try to optimize for power savage there. So what you see here might not be the numbers you see tomorrow. We're always trying to make them better. Okay, so first to start off, I figured we would give a view of a normal boot process. And then we have something to compare with when we start looking at the ULP. So if you see here at the beginning, where you see the number 1, that's the ROM bootloader booting up. And then it goes up to number 2 there at around 40 milliampere. That's where the secondary bootloader starts. And there you can see it sticks around 40 milliampere at number 3, where your main CPU for the app starts up. And then it just keeps going until number 4, where your actual app main and the user program starts. And as you can see here, the whole time the power hovers around 40 milliampere. So how does this compare with the ULP? Well, this is an example where we're running the ULP with the timer. As you can see, there's 2 spikes here. That's the ULP waking up. Here, I think it's around 750 milliseconds between each wake up. And as you can see, when the ULP is not running, we're idling at around 9 microamps. And then if we zoom into one of these peaks where the ULP is running, we can see that we're running at around 400 microamps. So what the ULP here is doing here, it's waking up, and then it's wiggling some GPIOs, and it says, oh, it's time to go back to sleep again. And we go back down to 9 microamps. So compared to the 40 milliamps when the main CPU was running, this is, of course, a massive difference. So if you're able to utilize this instead of the main CPU, there's a huge advantage there. Here is another example where we're running a ULP taking ADC measurements. Here we can see that the idle current is actually much higher than the previous slide. And this is because currently when you're running with the ADC, there is some extra settings required that increases the minimum current. And this is also something we're working on improving. Okay, and then how does the future look for ULP? In IDF 5.0, which is right now, the ULP FSM is fully supported on ESP32, S2, and S3. And the ULP RISC-V is partially supported on both S2 and S3. So the basic functionality is there, and all the examples you saw is there, but not every driver is supported yet. What is supported is the ADC driver and a few different utility drivers. And for the near future, aka the upcoming half a year, our goal is to keep on expanding this support. We want to aim for a full support for the ULP RISC-V on both S2, S3, all features, which includes interrupt handlers, I2C driver, and the temperature sensor driver. And what do we have upcoming after that? Well, the most exciting thing is the C6 that's getting released in the future. And the C6 has a low power focus. And some of the improvements there is a new ULP core. It will be a RISC-V IMAC core with a 20 megahertz clock, a two-stage pipeline, which means this core will be faster than both the S2 and S3 ULP RISC-V. It will have JTAG debug support, so now you can actually see what's going on your ULP core. It will be able to access all of SRAM. Of course, you won't be able to use the SRAM while sleeping, but it can give you some extra stuff to work with when the main core is awake. It will also come with a low-power UART, which is like a new RTC peripheral we're adding. And then it will also have access to all APB peripherals. And just to emphasize, this is based on our current engineering sample for the C6, and this, of course, might all change before the final release of the C6. So if you found anything in this talk interesting, or you want to play around with the ULP, here are some resources. We have our documentation, a few links there to sleep modes, the ULP FSM, the ULP RISC-V. And as Sudeep mentioned earlier, are examples. You can just compile them, run them, and get a feel for the ULP. And it's definitely the best way to go about learning about any of the IDF features we have. And if you want to contribute, I think the ULP is actually a nice feature. It's very isolated, and our software support on this is still not that mature. So there's a lot of things you can do there to help us. You can help with reporting issues. If you want to contribute code, we welcome that as well by doing a pull request. And if you have any feature requests, either for new hardware or software, we're also happy to take that. And all of this is, of course, on GitHub under the ESP IDF project. Yeah, that was the end of our talk about the ULP. And now we can take some questions if there is any.